Hello and welcome to this video. So now we'll be officially starting the unit on ideal gases, and ideal gases are exactly what the name tells us what they are. So this is basically an ideal, a theoretical construct that we have that we use to describe the property of gases, and it does not apply most of the time to gases that we see in real life, but having some sort of a base reference is good because then all the other gases that we'll ever encounter we'll compare with respect to how an ideal gas behaves. So by the way, we can say a gas behaves ideally if the pressure is low and if the temperature is very high above the boiling point. So it's going to stay a gas, it's not going to become a liquid anytime soon. Right, so the pressure must be as low as possible, the temperature must be as high as possible for a gas to almost replicate ideal gas behavior. So before we actually go on to talk about ideal gases and the math behind this, it's also important to understand what are the assumptions or the postulates which are in place and why are ideal gases ideal. What are these assumptions we make which cause them to be ideal and not a real gas? So the first assumption is that all the gas molecules are in constant random motion. So what we say is that all matter is made up of particles which are in constant random motion. Right, so they're always moving, never at a moment's rest, and random means we cannot predict how a certain gas molecule will be moving, or if we are talking about a direction, in which direction a certain gas molecule will be moving, right? So this is one of these. The next one is that these molecules have negligible so we can ignore the intermolecular forces of attraction, or rather we choose to do this according to the conditions given above, which is that the pressure must be as low as possible and the temperature must be as high as possible, and we'll also see how this relates with this just in a while. The third one is that the molecules are moving in straight lines between collisions, right? So when they're not colliding with each other, they're moving in a straight line. So this is between collisions, and we'll also be talking about what happens in collisions in a while. So here, if we then go on to talk about the fourth one, which is now going to be related to collisions. So the idea is that the molecules behave as hard elastic spheres. So it's not like a ball which is made out of sponge, so it cannot change its shape, and it's elastic, and this is something we'll be talking about now. And this must already be ringing a bell with you if you remember your AS momentum. The next one is that the time of collision is negligible. So because these are hard spheres and not so they don't undergo any changes of shape, so when these collide with each other, when they come into contact, they almost instantaneously rebound again. So the time of collision which is spent is almost negligible. So the sixth one, which then actually relates to the collisions, is this, that collisions between molecules are perfectly elastic. So for this you need to remember just a bit of your AS momentum. So if you remember elastic collisions, then those are the collisions where there is no loss of kinetic energy, right? So in this one, there is no loss of kinetic energy. So if, for example, if a molecule collides with another one, the kinetic energy is conserved. The last one is this, and this is often asked in calculations and stuff like that. So the volume of the molecules themselves are negligible compared to the volume of the gas, or what you can also call the volume of the container. Right, so the size of the molecules are so small, and also because the intermolecular forces between them are so small, so the spaces between them are so large that the volume of the molecules is almost negligible compared to the volume of the container itself. And this will come into use later. So now, having laid down these assumptions that are in place when we talk about ideal gases, now let's go on and talk about the gas laws, which actually then give rise to what an ideal gas is. So the first one you might already know as either Boyle's law, which basically says this, that for a fixed mass of gas, the pressure of the gas is inversely proportional to the volume. So by the way, at this stage you are also expected to understand how the pressure is exerted by a gas. So the idea is really this, that when the molecules collide with the sides of the container, so they experience a change in momentum, which automatically then also leads to a force which is being exerted on them. And then they also exert a force by Newton's third law on the sides of the container, and that is per unit area, so that causes some pressure. So this is like some prerequisite knowledge that you must also be having at this point. So if we want to remove the sign of proportionality, and if we just multiply by a constant, so if we write this as P equals to K upon V, so we can also say that PV equals to K, which is nothing but a constant. And another way you might have also seen this very equation written is like this. So the product of pressure and volume at some values of pressure and volume must also equal the product of pressure and volume at some other values of pressure and volume. So their product is always a constant, and by the way, this is the very definition of inverse proportion. So if we talk about what's the reasoning behind this, so the idea is that when the volume decreases, so the molecules come closer together, and when the molecules get closer together, they also get closer with the container, basically. So what we say is that the frequency of collisions increase. Focus on my words very carefully. I'm not saying that the molecules move faster. I'm saying the frequency of collisions increase. So now in the same period of time as compared to before, you have more collisions. And then basically if the frequency of collisions increase, so basically you can say that there is a greater force exerted by the molecules as a whole. So then we can also conclude that the pressure increases. So this is like the explanation in words. Sometimes you might also be asked to explain this with the help of some graphs or whatnot. So there are these three graphs which are asked most often. The first one is a basic graph, which is just a graph of inverse proportion if you think about it. So if pressure and volume are inversely proportional, the graph shape looks like this. Like this approximately. So the curve does not touch either axis, and this is a curve of decreasing gradient basically. So this is the graph shape, right? So at some constant value of temperature as well, this is also important to understand that when we are talking about P, V and T, if you're looking at the relationship between either two, the third variable is constant, and additionally, as we said above, the mass of the gas is also constant. So this is at some temperature. Let's say this is T1. And what happens basically is that if you have temperature rising, so you have the exact same graph shape, but now it's going to be shifted like this. So this is now going to be T2. So the idea is basically this, that for the same volume, if I just mark that, so for the same volume, the pressure is greater at the greater temperature as well. So this is the idea, and in a while we'll also be looking at why this is so, why pressure increases with temperature in another law. The other graph which is asked is something of this sort. So if you have pressure, and instead of on the x-axis, instead of the volume, if you have 1 over the volume, so a reciprocal of the volume, so the graph just becomes a straight line passing through the origin, right? Because if you just look at this equation, if this is pressure is inversely proportional to volume, and if I take this to be another variable, let's say this is some variable z, so I can say P is directly proportional to z, and that z is really what I have on the x-axis. So then this just becomes a graph of direct proportion. A third graph which is sometimes asked is if you have the product of PV on the y-axis, and on the x-axis you can have either P or V. So in this case, since PV is a constant here and it does not change with any values of pressure or volume, this is just a horizontal line like this. So a graph like this is what you get. Now let's go on to another gas law. So the second one that we'll be talking about now. So before going on, let me just write this, that this law was for fixed mass and constant temperature, right? So whenever we are talking about two variables, the third one is assumed to be constant, because that will then also impact the relationship. So the second one is then called Charles' law, named after the scientist. Also known as the volume law, which just says this. Again, this one is also for a fixed mass. And right now, if you're talking about volume and temperature, so this is at constant pressure. So here P is not changing. So what this says is that the volume is proportional to the temperature, right? So this is directly proportional now. Now again, if you want to get rid of the sign of proportionality, we just go ahead and multiply by a constant. And here again, if we make the constant the subject, so we can say V upon T is a constant. So the ratio of volume to temperature, or even if you reverse it, temperature to volume, that would also be a constant. And this is also sometimes written like this, that V1 over T1 is V2 over T2. So some volume and some corresponding temperature, the ratio of that would also be equal to some other values of volume and its corresponding temperature. So the reason for this is basically that when the temperature increases, we say that the average kinetic energy of the molecules, that also increases. And when that increases, so the molecules move further and faster. So when they move faster and further, what they do is they spread out and occupy space. So that spreading out causes the volume to increase as well, right? So this is how they are related. Now the graph for this is this, which is that for some volume and some temperature, the relationship is direct proportion, so a straight line passing through the origin at some value, let's say P1 of the pressure of the gas, which is supposed to be a constant. Now if the pressure of the gas decreases, so if the pressure decreases, the graph is going to become like this at P2. So what this really means is that at the same value of temperature, the lower pressure gas P2 also has a lower volume than the one at a greater pressure. So if at the same temperature, if we can see obviously that V1 is greater than V2, so this volume is greater than this one, so that must mean then that the pressure of 1 must be less than the pressure of 2, right? So that's basically that inverse proportion that we're talking about here. So in this case, when the pressure increases, the gas has less volume at the same temperature. Let's go on to the third one now, which is called Gay-Lussac's law. And this one is also known as the pressure law. So now we're going to be talking about the relationship between pressure and temperature. So again, when we're talking about pressure and temperature, as it goes, all of these are for fixed masses of gas. And in a while, we'll also look at how the different variables change with the amount of gas which is present. So for a fixed mass of gas, but then additionally, because this is talking about pressure and temperature, so this one also assumes constant volume. So for constant volume and a fixed mass of gas, the idea is that the pressure is directly proportional to the temperature. And now this is pretty self-explanatory, that P is kT, and then we can say P upon T is a constant, and then we can also write this as P1 over T1 is equal to P2 over T2, right? Again, the same ideas here. And the reason for this is that as the temperature goes up, again, it's the same thing, that the average kinetic energy of particles increases. So average kinetic energy increases. So again, the molecules will move further and faster. Here we are more interested in the faster part rather than the further part. If you remember, then we used the further part in the previous explanation to explain why the gas molecules spread out. So when they move faster, again, the idea is you have more frequent collisions with the sides of the container. So more frequent collisions with the container, which is really what pressure is. So a greater force is exerted, causing the pressure to rise as well. Now in this case, the graph for pressure versus temperature looks like this. Again, directly proportional. So we expect a straight line passing through the origin, again at some constant value of the volume. Let's say if we have some other value of the volume like this. So we can see here that at the same temperature, this volume is less, this pressure is less, so some P2 is less, this is a greater pressure. So we can see that if P1 is greater than P2 here, so then if you think about the relationship between pressure and volume, this must then imply that volume 1 is less than volume 2. So this one is greater, right? So at the greater volume, for the same temperature, you have less amount of pressure.